Seismic anisotropy in the Earth interior can be a product of an intrinsic or an extrinsic origin. In the Earth's upper mantle, intrinsic anisotropy results from the crystallographic preferred orientation of minerals due to mantle deformation. Contrastingly, small-scale isotropic heterogeneities can be mapped as extrinsic anisotropy due to finite frequency seismic data. Surface wave tomography images positive radial anisotropy underneath oceanic basins characterized by a layer of strong signatures in between 80 to 200 kilometers depth. Although there is already a consensus on the anisotropic origin of the asthenosphere, lithospheric anisotropy is not yet well understood. For instance, it is argued that the positive radial anisotropy across the oceanic lithosphere results from the transportation of the CPO developed below the ridge. Others argue that the melt structures preserved during the thickening of the lithosphere can also explain the signature of anisotropy. Hence, it is essential to discriminate what contribution comes from CPO or small scales. Elastic homogenization provides means to achieve this goal. What you see on the left is a cartoon depicting homogenization. Here, isotropic layering produces seismic signals identical to those of radial anisotropic structures. In 2018, Capdeville and Metlivier showed that assuming a perfect data coverage, a homogenized model is the best possible model one could achieve from tomography. What you see below is an isotropic marble cake model of the mantle. Notice that upon homogenization, horizontal layering is registered as positive radial anisotropy, whereas vertical layering corresponds to negative radial anisotropy. What happens if we homogenize a CPO model alone? As we can see, small-scale features in intrinsic anisotropy are smoothed out as a result of the averaging process. So I urge you to read the paper because there we showed how we came up with a composite law for radial anisotropy. Supposing that we have a tomographic model of radial anisotropy, we verify that this effective psi is a product of the psi obtained from a homogenized CPO model and of the psi due to small scales. Apart from verifying the law, the figures on the right tell us that it is imperative to homogenize a CPO model first before drawing comparisons with a tomographic model. Here, we can see that, so in this figure, we can see that the tomographic psi and the homogenized psi CPO converge toward the true psi CPO at indefinitely small wavelengths. Only in this unrealistic case, that is, the perfect recording of the seismic wavefield up to infinitely short periods, would seismic tomography be able to map this through intrinsic radial anisotropy. At wavelengths longer than the scale deformation patterns, tomography underestimates intrinsic anisotropy due to spatial averaging. At shorter wavelengths, tomography overestimates intrinsic anisotropy due to the presence of extrinsic anisotropy. So we attempt to use the composite law to separate the intrinsic and extrinsic contributions of radial anisotropy in a plate average tomographic model underneath oceanic basins. The tomographic psi is crudely estimated by dividing for each pixel VSV and VSH inferred from surface waves. Models A and B are psis obtained from CPO models corresponding to fast and slow evolving textures respectively. Models A star and B star are their homogenized counterparts. By dividing for each pixel the tomographic psi over models A star and B star, we obtain our SPA models of psi that solely pertain to small scales. Thank you very much.